Hello everyone, and welcome. Have you ever been in a chemistry lab and seen someone press a small, clear disc to analyze a sample? Or have you wondered how scientists can see the building blocks of a molecule using invisible light? Today, we're diving into a key technique called FTIR spectroscopy and answering a very specific question: why is potassium bromide, or KBR, so commonly used? To understand this, we first need a quick idea of what FTIR does. Imagine you have a sample, and you want to know what it's made of. FTIR, which stands for Fourier Transform Infrared Spectroscopy, shines infrared light through that sample. Different parts of the molecules in your sample will absorb different frequencies of this light, causing them to vibrate and stretch. The machine detects which frequencies are absorbed, creating a unique spectrum that acts like a molecular fingerprint. But to get a clear fingerprint of your sample, the material holding your sample must be invisible to the infrared light, and this is where KBR becomes the star of the show. There are several key reasons for its widespread use. First and foremost, KBR is transparent to infrared radiation over the most important analytical range, typically from 400 to 400 wave numbers. This means the KBR itself doesn't absorb the IR light, so it doesn't create its own confusing signals or block our view of the sample spectrum. It's like using a perfectly clean, clear window to look at a landscape. A colored or dirty window would ruin the view. The second reason is that KBR is chemically inert. For most organic compounds, it acts as a neutral bystander. It won't react with your sample, which is crucial because you want to analyze your original material, not some new substance created by a reaction. Third, KBR has ideal physical properties for solid sampling. It's a relatively soft, crystalline salt that can be ground into a very fine powder. To prepare a sample, you mix a tiny amount of your solid compound with a larger amount of dry KBR powder, grind them together thoroughly, and then use a hydraulic press to squeeze the mixture under immense pressure. This pressure causes the KBR to flow and fuse into a small, transparent, glass-like pellet with your sample particles evenly trapped inside. This KBR pellet is sturdy enough to be handled and placed directly in the path of the spectrometer's IR beam. Of course, KBR isn't perfect. Its main weakness is that it's hygroscopic, meaning it readily absorbs moisture from the air. Since water has a very strong IR absorption, this can interfere with the results, which is why KBR must always be kept extremely dry, often in a special oven or desiccator. So, to sum it up, KBR is the go-to material for solid-state FTIR because it's transparent to IR light, chemically unreactive, and can be easily pressed into a perfect pellet to hold the sample for analysis. Thanks so much for watching. If you found this explanation helpful and learned something new, please hit the like button and consider subscribing to help support the channel. Your support allows us to keep making more science content. See you in the next video.